I will do this recording in 3 parts. First, I will do an introduction, terminology, and basic trees in one recording. And then in the second recording, I will go to binary trees. And then thereafter, I will do a recording on ordered binary search trees. So let's kick off with the introduction then. A tree is a hierarchical structure. Here we have an example of such a structure, the organogram of a university. Please note that this is not complete, by all means not complete. There are many nodes missing. This is just an example. So in this example, we have the rector. He has children or people reporting to him, vice rector academic, vice rector research, vice rector operations. In turn, the vice rector academic has deans reporting to him, the dean humanities, dean natural sciences, dean law. The dean natural sciences has children reporting to him, HODs. There are 4 listed. Of course, there are many more. The HOD CSI has here 4 lecturers listed. Of course, there are many more. I would be one of them here down at the bottom at the moment. Previously, I was privileged to be there. So please note that this vice director research, it looks like she's a leaf, but she is not. Because this is not complete. There are many leaves here not shown. But in this specific example, this is a leaf. A leaf is a node without children. And there are also leaves here and there, leaves here at the bottom of the tree that do not have children. So if we have a look at the terminology, we refer to the root as the single entry point. There are no cycles, so you cannot move from the rector to the vice rector academic, dean natural sciences, and then back some way to the rector. There's only one way of moving from the root to a leaf, not from a leaf back upward. So there's no cycle possible. There's no reverse movements possible. These connections between nodes are referred to as paths. The connections between nodes are referred to as edges. A combination of edges is a path. So that's a single edge. But if I want to go to, let's say, lecturer 2 from the rector, I have to follow a path down there. Now, there's only one path from any node to another. There are no duplicate paths. There are no multiple paths. There's only one path possible from a node to one of the leaves below it, one of the children below it. Yes, we said that a node has children, but in reverse, a child has a parent. That is the node above it in this organogram or hierarchical structure. Then we have the depth and the height and the degree. These are 3 different terms that we need to understand. The depth is of a node, the height is of a tree, and the degree is of a node again. So make sure that we know that we refer to the correct entity when you refer to each one of these terms. So the depth of a node is the length of the path from the root to the node. So if I look at HOD chemistry, I will have 1, 2, 3 paths or edges to get there from the root. Note that it is not the number of nodes, it is the number of edges from the root down to the HOD chemistry. That is the depth of a specific node. The height of a tree is the maximum depth of all its nodes. So if you look at all of the nodes, all of them, and you calculate the depth of all of them, you will find that these leaves here at the bottom, they are the deepest, and they are 1, 2, 3, 4 edges away from the root. So there, the depth of this tree is then 4. The height of the tree is 4. The degree of a node refers to the number of its children. So that is simple. Direct children. So the degree of the vice rector academic is 3. The degree of the dean natural sciences is 4. The degree of the dean humanities is 0, etc. The number of direct children of a node is referred to as its degree. Now let's have a look at another example. In this case, we have a basic tree. This example comes from Nykov. Every node has an int value and 0 or more child nodes. Now, this is very important that we understand that a tree is used to carry data. So we need to be able to save data in the nodes, and we will show how we are going to do it just now. So this tree carries int values in no specific order, and that's important to mention, in no specific order. So later we will get to nodes that carry data in a specific order, but in this case, no specific order. So if I have to set up the data structure for my tree, first of all, I make sure that my tree is generic. In other words, I can save any data type in there. In this case, we have a class int, but of course it can be anything else. Then inside my class, I have a property value of this type that the generic type of the tree is. So this is the thing that we will save in the tree. This is the data that we are interested in. Of course, private set, because we can only set this value through the constructor or through an add method or whatever the case may be, but not directly from outside. The class user may not set this value directly. And then another property that we need is that of the list of children. Now note this embedded structure. We have a list that's a normal generic list. In this case, we can use the .NET list. That's easier. We do not have to use our own list, although you can. And then inside this list consists of nodes, and every node in turn consists of a value of type T. So note the embedded structure of this property. It's a list of children, but every child in the children consists of a node, and every node consists of a value of type T. So I mentioned the idea of a generic class. Here is my method to add children. And this is a simple matter of taking a child parameter, and this child parameter is of a tree T, not T. Note the difference. And then all that we need to do is to just use the list of children and add to it, and that's a normal add method that we are used to for lists. The constructors, there are two constructors. The one is a bit more involved than the other. This first one is a simple one. This constructor takes a value T, and then we need to instantiate this value. In other words, assign a value to the property value, and then we have to instantiate the children. Now this does not add children to the tree, it only creates a list of children. It's also important that we understand that this tree is a recursive thing. If we go back to our diagram, every node in a tree is a tree in itself. I repeat, every node in a tree is a tree in itself. So here we have a node 7, and that is the root, and it has children 19, 21, and 14, but each one of these children are trees in itself, because 19 is a subtree with root 19 and children 1, 12, 31, etc. 21 is also a subtree, the root is 21, no children. 14 is a subtree, the root is 14 and children 23 and 6. And so also for these leaves at the bottom, each one of them are also trees. One is a root of a subtree and it has no leaves. So make sure that we understand that the tree is a recursive structure with nodes inside nodes inside nodes. And each one of these nodes is actually a tree in itself. So if we call a constructor, we do this constructor for each and every node. And, sorry, not here. We call this constructor for each and every node. So this will mean that we call this for the other nodes as well. And this is exactly what we have done here with create tree method. So first of all, we created tree with a value 7, and that value will go in there, and it will assign this value to the value property of the tree. And then we also create a tree for 19 with value 19. So we create a tree there, and then we also create a tree for, let's say, for 1. So the value is 1. It's a tree that we create there. So when we create nodes, we create trees, and then later on we can link these nodes to each other with this add child method. So look at the example above. maybe I should split the screen. Then we can have the picture and the method available at once. So if I now look at tree 7, I can add children 19, 21, and 14. Add child 3, 19, 21, and 14. Tree 19 is a root in itself, and we add children 1, 12, and 31. And tree 14 is a root in itself, and we add children 23 and 6. So in this way, we link the nodes to each other. So the linking of nodes is left to the class user. It's not done in the tree, in this specific constructor. So we use the constructor just basically to create the tree or one of the subtrees and instantiate instantiate a list of children, and then the class user will use this. So if we have a look at the real example in Visual Studio, let me just bring it over here. So this is my example in Visual Studio. I have a program that is my class user, and the tree that is the class I'm working on. Now this tree is generic. It has these two private properties. It has constructors, and now this is the constructor we are currently busy with. And if I now go to my program class, this is how this constructor is used. So I assign create tree 1, and then in this method here, and that's the one that I just shown in the tutorial document, we create the trees as separate nodes, and at this stage all the nodes are separate, and then we start linking them the one to the other in the structure as necessary. So this linkage is left to the class user. The second constructor is one that it does everything in one go. So it takes the value as the previous one. In that regard, it's the same as the previous one. It takes the value as the previous one, but then also it takes an array of children. So what this thing does, it calls the basic constructor in turn, and the basic constructor will assign the value to the value property, and the basic constructor will also instantiate the list of children, but it will not add children to the tree. But now what is done extra in this second constructor is to add children. So it steps through this array of children in the parameter and then add them one at a time to the tree. The class user will now have a bit more complicated work to do, because this is what we can do from the class user side. We create a tree, its value is 7, look at the picture above, and then the second parameter would be an array of trees. And in this case, we will have 1, 2, 3. There are 1, 2, 3 children. The values of these trees are 19, 21, and 14. And then this one, in turn, also has a list of children, which will again be an array of trees with values 1, 12, and 31. That one goes on its own. And then 14 will have an array of 2 children, 23 and 6. So you can imagine that if this tree is deep with several layers, then this way of constructing a tree can become complicated and can become confusing. So this is a possibility, but it's very seldom used, because it's easier to just go one at a time, even though it might be longer, to just go one at a time and link the children as needed. So that is the second constructor. Now, a very important aspect of trees is the way to traverse a tree. Now, the word traversal refers to visiting or locating, or just visiting each one of the nodes in the tree with a very specific condition. First of all, we should visit all nodes in the tree. No node should be left out. And secondly, no node should be visited more than once. So every node should be visited only once. And we have different strategies to do that. And The first strategy that we can discuss here is the breadth first. We also have depth first, and then with the binary trees we will get to strategies in order, post order, pre-order. We will discuss that when we get there. So first of all, a breadth first traversal looks at the tree starting from the root and then visit all the children on the first layer, on the first level, and then it visits all children on the second layer, etc. So the order of visits of the nodes in this example tree will be 7, 19, 21, 14, 1, 12, 31, 23, and 6. So that's a breadth first, starting from the root, then going to the next level from left to right, then going to the next level from left to right. So we can do it with a queue in a non-recursive way. Where's my breadth first? Here it is. So this is my breadth first traversal. It's non-recursive. It uses a queue. Now it's difficult to explain this thing. In just explaining it, we just have to in Visages I can maybe let us do this and add a new document, and let's insert a table of let us do this. I have a table that will be my queue, but before I get to the queue, let us take this example and copy it in there. So I think this should be okay. So the first thing that we need to do is to visit the root. So we enter the root in there in the queue. The next thing that we need to do is to visit all the nodes of this root. So we will visit 19, 21, 21, and 14. And then once we have done that, we dequeue this one. So we take that one out. I'm just going to scratch it out. So I hope that you maybe it will be more visible if I just recolor it. So let's just do that. So the red means it's scratched out. It does not exist. It's dequeued. So now I visit my 19. The first thing that I do when I visit the 19, I add its children. That will be 1, 12, and 31. 31. And then I dequeue the 19. The next thing that I do is to take the 21, that is the next visit, the next node in my queue, and I visit all its children, and there are nothing. So all that I do is to dequeue it. Then I take my 14, that is this one from the queue, and I dequeue it. I first visit its children, 23 and 6, and then I dequeue this 14, the first one in the queue. That means that it's gone. The first node is now 1. So next thing, I take this one and I visit all its children. There's none, so I just dequeue it. The next thing, I go to the 12, visit its children. There's none, so I just dequeue it. Then the same goes for 31, visit its children. There's nothing, so just dequeue it. 23, visit all its children. There's nothing, so just dequeue it. And then 6, visit all its children. There's nothing, so just dequeue it. And in this way, I have visited all the nodes in order. So check that the order of the nodes in this queue is the order of a breadth first traversal. And we stop when the queue is empty. That is important. Now remember, this queue is empty because all the nodes are red. I have dequeued all of them. So we stop when all the nodes, when the queue is empty, then we are done. So this is the breadth first, and this is the algorithm to do that. We use a queue. Every time that we visit a node, we add it to a list. So first of all, we have to instantiate a list, to create a list. That's our queue for a start. So we enqueue the root, and then we have a loop. So we carry on with this as long as our queue is not empty. So since the queue is not yet empty, we dequeue from the queue. We put that dequeued value in a current temporary variable, put that value inside the list, and then step through all the children of this current node. and add them one at a time in the queue by enqueuing them. And we carry on like this until this queue is empty. And then once we are done with that, the list of nodes will contain the values that we need, and that will then be returned as part of the breadth first search. So note here that we add the value of the nodes to the list, not the node itself. So only that part of the node is added to the list in the breadth first. We should always remember when we work with a node in its entirety and when we work with a value in this node. There is quite a difference. Please don't get confused. So this breadth first will then be called from my class user side. Where is it done? Here. So I can now write all the nodes in a breadth first order by calling this BFT method, breadth first traversal method from the tree, assigning, and this thing will return assign to a list of nodes, and then I can just write down the nodes in a console write line statement as we have in this example. So that is a breadth first traversal of the nodes in my tree. I got a question about this keyword, that keyword. What does that thing mean? Well, that refers to the object that calls the method from outside. So in this case, BFT is called by this tree variable, and tree variable will be tree7. That will be the root. So this is what is returned by create1. So my tree variable will have the value 7, and if I look at my picture, that is the root of my tree. So if I go to this keyword, that is what that thing will refer to. Now, depth first traversal, if we look at the picture here, is a traversal that starts at the root and then go as deep as possible. So in this specific case, we will have 7, 19, 1, 12, 31, and then back up, go 21, then 14, 23, 6. So we will go as deep as possible, and the nodes on the same level will go from left to right. So 7 from the root, 19, 1. Then we go back to 19, but we don't visit it again because we have visited it already. But just go to his next child, 12. Go to 19 back, but don't visit it. And then next child, 31. Then go back to 19, no more children. Go back to 7, visit the next child, 21. Go as deep as possible, but there are no children further, so we go back to the root 7. Then 14, 23. Go back to 14, don't visit it because we have already visited. And then 6, and then we're done. So this is a depth first traversal. Now, a typical way of doing a depth first traversal is by using a recursion. So recursion always, mostly go with two methods. So we have a public method and a private method. Now, the public one is accessible from outside this class. From the class user side, we can access it. It does not have parameters, and this one has 2 parameters. So it's important that the parameters differ, the signature must differ, otherwise there's confusion, and Visual Studio will not know now to which method you refer to because they have the same name. So it's an overloaded method, but the one is public, the other one is private. This one has no parameters, and this one has 2 parameters. So from outside, we call this method, and then from within this method, we call this private one. And the private one in turn calls itself until it's done, and then it returns control back to this public one, which will then return back to the original initiator of this procedure, namely the class user. When we kick off with the public version, we have instantiated a list of nodes, which will eventually carry the list of nodes that we want to visit. Then we go to the private version of the depth first traversal with this list of nodes. Currently it's empty, but when we go in here and this thing does its job, when it returns, there will be nodes in there, there will be values in there, and that will then be returned to the class user. The class user, if we go to the live example, That is the depth first traversal, the Visual Studio. Let's go to the program. The class user will just call it like this. Assign the return value from this depth first traversal to a list of nodes, and then display this list of nodes in whatever way he wants to. So this is the depth first traversal. The depth first traversal says, all right, let's use a stack. Sorry, this is not, that's the search. I always get confused between the search and the traversal. The one is DFS, the other one is DFT. Let's go there. There's my depth first traversal, the DFT one. That's the basic depth first traversal algorithm, the basic recursive one. It starts off by adding this node that comes in to the list of nodes, and we only add the value. This thing is a list of t, not a list of tree. So it's a list of t, and it adds the value in the node to this list. And then it steps through all the children of this specific node, and in turn, for each of the children, it calls the DFT in turn, this depth first traversal method. So that is the depth first traversal method. So the next thing that we will have to discuss is then a depth first search, and a search is different from a traversal. A search says, I want to find a specific node in the tree, and the moment that I found it, we stop the further traversal. We do not go further, we found it. And if it's not found, then we, let's say, return a false or whatever we want to. So in this depth first search algorithm, we return a path. So that will be the path. This list of nodes will be the path to a specific node. So if I want to, let's say, find 31, I go 7, 19, 1. No, it's not that one. 7, 19, 12. It's not that one. 7, 19, 31. Ah, that's the one I need. So the path will be 7, 19, 31. And this list will contain the path, the list of nodes that constitute the path from the root to the wanted node. So in this case, we will use a stack. Again, we have two methods, the public and the private one. In this case, we will use a stack. So the stack is empty. We will pass the stack to my private version of the depth first traversal method. And then every time that I get in here, I will push my node that comes through there. I will push the value of that node to the stack. Note the stack is of type T, not of 3T. So I push the value of the node to my stack. And then in the same way as for normal depth first, I visit all children. And then again, I pop my value from the stack. But there are conditions. First of all, if I did not find my value yet, I can do this. If I found the value, yet I don't do this depth first traversal, so the recursion is stopped. So no need to go further if I found what I've been looking for. So this is this first condition. And then inside my if, I have another if. If I did not find my value yet, I can pop again, because that's not the one that I've been looking for. So 7, 19, 1, no, it didn't like this one, so pop this one. 7, 19, 12, no, I don't like this one, so pop it. 7, 19, 13, 1, yes, this is the one I want, so don't pop it, and I'm done with my recursion. So when I call this in a depth first search algorithm here at the bottom, in this example, we find 23. What this thing does, it returns the path to 23 inside that list. And if I now run it, I will get the path to 23 is 7, 14, 23. 7, 14, 23. 7, 14, 23. That's the path to 23. So that is what we are doing with the depth first search. We put the path of the nodes inside a list, and then we can use that list as we want to. All right, so this is the normal basic tree.